All right, I'm gonna try and do this video fairly quick, just with a screen recording app here. We have got a lot of people who get pretty confused with torque and horsepower, torque at the crankshaft, torque at countershaft sprocket, torque at the rear wheel. There's a lot of misconceptions about a few things. First off, we can start with in an internal combustion engine. Like, I can probably Google a graph while I talk about this, but in an internal combustion engine, you typically have a torque curve. So let's say CRF 450R. See if we can see a graph here just to show it doesn't have to be really any. I don't really care what graph it is, but if you look at like a typical, we'll just use this, like hopefully the screen recording app is good enough. Maybe I can even zoom in on get the picture to open properly and make it as big as possible for everybody to see it, because I realize this screen recording app might not be great. It still didn't go much bigger, but you can see the torque and the dots here, which is the plotted dot line, would come down, and notice how their RPM scaling here starts at 2000 RPM. So if you were to plot this over, it would come down to 0 torque at 0 RPM. Internal combustion engines simply can't produce torque at their wheel. And here's another thing I was going to bring up. I actually used CRFs only, but this is a modern number. A 2020 CRF 450R produces 32.2 foot-pounds of torque at the crankshaft. That's very critical to understand that. That's at the crankshaft. But it's also peaking the torque around 6,900 RPM. You can see the torque curve here. It starts at 0 RPM, climbs as the engine's actually running, because it can't even produce torque at 0 RPM. And then once it's idling at like 1,000 RPM, there's maybe 2 foot-pounds of torque there. There's not much at idle. And once you come off idle, you can actually produce meaningful torque, which actually means it can move the bike. So you can see the peak here, and then it falls off as it comes towards the red line. So to come back to like my dyno graph here, on an electric bike, this is from my CRF that's been converted with the 0 SR motor and SR controller, and then a 2019 long brick, which would be in an FX, 0FX, or sometimes they put 2 of the long bricks together in a SR or SR, and I think it's in the SRF as well. If you were to plot this over, you'd probably see somewhere around 105 to 110 foot-pounds of torque at just offered at 0 RPM. Essentially with this, you can kind of see the torque is slowly falling. The reason my dyno, and there's a lot to this video, a lot of little details that I'm going to try and cover in this video, and try not to forget anything, because I always seem to leave something out and then have to come back and answer questions in the comments, or maybe answer questions wherever. But my dyno produces a torque reading at around 1,000 RPM that you can actually trust. The reason it starts off below that is I've actually set my dyno to start the measurement at 900 or 8 or 900 or 1,000 RPM or whatever it is, because below that there's not enough good data. And the reason for that is I have 12 teeth on my tone ring on the actual dyno roller. And what that is there's 12 samples for RPM measurement that happen every revolution of the dyno roller. And the dyno roller, I believe, is just over 18 inches outside diameter. I got to double check that measurement. It doesn't really matter. It's just an example so you have a rough idea. What I'm going to do eventually is switch to a tone ring that has 4 to 5 times as many teeth. The reason for that is with 4 times as many teeth, my dyno run could start at 250 RPM, which would be down here. So I'd be able to get accurate data starting around 250 RPM, and then we'd show a little bit more torque. I'm not super concerned, because I know this motor and controller combination typically produced, depending on the year, and with the IPM motor, I believe it was 110 foot-pounds of torque at the motor, but it might be 106. I can't remember. I know the SRF originally was 106, and I believe that was when it was surface mount magnets. I think the IPM was a little better. Either way, it's right there. 106, 110, that doesn't matter. This bike has more torque than I can handle. Like if we actually switch this to results versus speed, I believe my speed right here, I just upgraded my Dyno software, so I have to actually probably change something there, but my speed right here is somewhere around 95 kilometers an hour, I believe it was, because I know my speed up here is 160 kilometers an hour, so it's half a 160 divided by 2 would be 80 kilometers an hour, so 3,500 RPM. I guess right here is about 85 kilometers an hour. So yeah, okay, that's right. I remember doing the other video now. I think it's more around 4,000 RPM that I hit about 60 miles an hour or 100 kilometers an hour. That's where it starts to be, you know, you're just at a point where it can still power wheelie, but it has to be a fully charged warm battery on a nice day kind of thing. But below that, you know, anything below 80 kilometers an hour, you hammer the throttle and the front end's in the air instantly. And that's because it has a ton of torque. So at the motor, I'm producing, you know, over 99 foot-pounds of torque at the actual motor. My gear ratio is actually 5.833 to 1. And we can just do a bunch of threes times, let's just say it's 100 foot-pounds of torque, because that's what we proved on the graph. That's 583 foot-pounds of torque at the actual rear wheel. And that's with a 24-inch outside diameter tire. And that's roughly what I have. I think I'm maybe a smidgen over that. But that means if you were to take a torque wrench, for instance, and actually set it to 583 foot-pounds and actually hook it to the center of the rear sprocket, you would actually be able to apply the throttle and to make the torque wrench click. Or if it's a vibrating torque wrench, whatever, it would set the torque wrench off at that point. In fact, it would actually be a little more, and we're more around 110. So when you do 110 at 0 RPM roughly, or maybe 1 RPM, because some motors won't produce their full torque until it just moves a smidgen. They'll produce almost full torque at 0 RPM, but some need the actual motion to produce full torque. Now you're dealing with 110 foot-pounds of torque at the motor, ends up being 641.6 foot-pounds of torque at the rear wheel. So this comes back to my other video where people are really confused about torque, because I displayed torque at the rear wheel and everybody says, well, there's no way it has that much torque. Well, it does. So now to go back and look at our CRF plot here, we have a max torque of 32.2 foot-pounds of torque at the motor, at the crankshaft of the motor. When you deal with an internal combustion engine, this is a gear ratio chart that CRFs only has online. This applies to 2009 to 2013. It's going to be very, very close for a 2020. They didn't change the gear ratios drastically between those two, between 2013 and 2020. If you're to look at these different gear ratios, what you have is you have 3 stages of reduction in an internal combustion motorcycle, motocross bike. You have your primary drive, which is actually your crankshaft with 23 teeth on it, and then your clutch basket has 63 teeth on it. So but the difference between the crank and the clutch is 2.739 to 1 reduction. Then you have whatever gear you're in. So it's going to be through the primary drive. Then if you're in first gear, 15 or 27, which is actually your output shaft, counter shaft, 27 teeth on that. And your first gear on your input shaft is going to be 15 teeth. So 27 divided by 15 is 1.8 to 1 reduction. So we can actually work the math on this. And then you have final drive, which factory gearing is 48 teeth divided by 13. Some people gear them down. They will go to 52, 53 teeth. And in my bike, I put a 55 tooth. It's the biggest OEM rear sprocket for a Honda I could find, because I wanted to gear my bike down as much as possible. It has a top speed of 160 kilometers an hour, which is 100 miles per hour. You don't need that on a motocross bike, but that's geared down as much as I could. So I can set the rev limiter lower, but you know, it depends on which mode I'm in. I have 3 performance modes. One is like a beginner mode. One's my daily riding mode, which is more for single track stuff. And then I have you know, all out balls to the wall that allows everything to happen, which would be more or less supermoto kind of stuff. Because if you have a fast track where you're hitting high speeds on supermoto, you'd want to be able to actually wind it right out to 100 miles an hour, maybe on that long straightaway. So to go through these ratios, you take your primary drive ratio, which is 2.739, times your first gear ratio. We're going to use first gear for this example. Times, so you multiply the three together, your final drive ratio, which is 3.692, and gives you an overall reduction ratio of 18.2 to 1. So then you come back to your actual torque, which is 32.2 foot-pounds of torque, and you bring up your calculator at 18.2 to 1 reduction. That gear ratio is a multiplies your torque to the rear wheel. So if you have, again, a 24-inch outside diameter rear wheel, which is close to what it is, we'll just use that for I just screwed up and lost my calculator on that other part. We'll jump back to CRFs only just to make sure I can actually, I apologize for that, but 2.739. I'm trying to do this unedited so I don't have to spend a bunch of time editing a video tonight. Times 3.692. So you have 18.2 to 1. That's what I thought it was. Come back over here to this. 18.2 to 1 times 32.2, which is the torque at the crankshaft, equals 586 foot-pounds of torque at the rear wheel in a CRF 450 from factory at 2020. Now, here's a couple catches. Remember, this torque curve is not flat. This torque curve needs you to keep it on the pipe, so to speak. You got to rev it up, slip the clutch a bit, get it into the torque curve, probably a little above 5,000 RPM before you really are applying all that torque to the rear wheel. And once you're above 62, 6,300 RPM, that's where you really start to see 550 plus foot-pounds of torque at the rear wheel. That starts to fall off past 9,000 RPM. You're still going to rev it out there. You're going to rev it up here, and then you're going to shift gears. You usually spend most of your... We need to make sure we're clear on this too. Torque at the rear wheel is actually what your acceleration comes from. If you apply 100 foot-pounds of torque to the rear wheel in a motorcycle, it'll accelerate at X amount of speed. If you apply 200 foot-pounds of torque to the rear wheel in the same motorcycle, it's going to accelerate at twice the speed, provided the front end's staying on the ground. It's not wheeling or not spinning, not any of that shit. Double the torque of the rear wheel means double the acceleration. Well, that's why you use first gear in a motocross bike to get off the line, depending on what you're doing. Maybe second gear if you're a lightweight rider and you're racing motocross, you have really good, you have the right conditions for it. But for the most part, you need some torque of the rear wheel. The other thing that this does, being in first gear, is excuse me, when you're down here and you're more around, let's say 18 or 20 foot-pounds of torque of the rear wheel, down around 4,500 RPM, whatever that number actually is there, you're actually going to be seeing around 400 foot-pounds of torque of the rear wheel. Well, when you're in first gear, that's still more than enough to actually get the bike to go really good. It's going to accelerate really good. 586 foot-pounds of torque applied to the rear wheel makes the front end come up in the air, makes it wheelie, or makes the tire spin, depends on what kind of conditions you got. So once we start to work through this, what you can do is you can come back here to the CRFs only section, and you can look at your ratios for all your gears. You can say, well, first gear is 1.8, second gear is 1.4, third gear is 1.2, fourth gear is basically a direct drive, it's 1.05 to 1, and then fifth gear is actually a bit of an overdrive ratio. Well, I took and I plotted that into a spreadsheet here just to kind of give you an example of what you have for torque at the rear wheel. So what this is this spreadsheet shows max speed in each gear and then peak torque at 32.2 foot-pounds of torque, and then their overall gear ratio. First gear, the overall, all three stages multiplied together, it gives you 18.205. Second gear, 14.873. Third gear's overall ratio is 12.493. all the way up to 5th gear. Overall ratio with all 3 stages multiplied together, that's how this works, is 9.194. Then what I did was I put peak torque at rear wheel in each gear, and I basically plotted this out in a spreadsheet. Well, you have 586 in 1st gear and all the way down to 296 in 5th gear. Then I plotted that out in a graph so you could see it. Now remember, this isn't 100% accurate, this graph. This graph should show the bumps of that torque curve that's not flat. If you remember coming back here, this torque curve is not flat. So it should have bumps, but I really didn't have the time to go put a bunch of different arbitrary numbers in here to give me the 5 bumps, one for every gear. So this is good enough for argument's sake so you can kind of understand. All the way up to top speed. Max speed in the top gear is 85 miles an hour, which is about right for 50. That makes sense. Well, if you look at my graph, I have something that starts really flat, produces an amazing torque. I need to put this back versus speed. If I can switch the bottom. I might have to do that later. Engine temp, gear ratio, speed. I don't think it's going to be easy for me to do right now. I think speed's going to be plotted the wrong way. Yeah, it will be. So we'll just go back to results versus RPM. That's good enough. The big thing is we know that, what was it, 3,500 RPM is about 80 kilometers an hour, which is, I have to work the math on that, but I guess that works out to be 50 miles an hour, right? So if you're to look at this and find what would be roughly 85 miles an hour, we're probably talking about somewhere around 4,600 RPM. I'm still producing 65 foot-pounds of torque at the rear wheel. So if we're to just quickly use a calculator, 65 times my gear ratio at 5.83333, I'm going to have around 379 foot-pounds of torque at the rear wheel at about 85 miles an hour. Well, if we come back to the CRFs, the other graph on my spreadsheet, well, they're already dropping down, and this is also another part of it's a little bit of a misconception here in my graph, because at max speed, your torque is what? Your torque is 0. At max speed, you're at the rev limiter and it's bouncing off the rev limiter. You have 0 torque. It's not trying to push you any faster. So yeah, okay, maybe 80. This actually should be slid back a little bit, but it's close enough just for our argument's sake, right? So let's call it 80 miles an hour. You're going to have maybe even 75 miles an hour, because you got to look for where that peak of that torque curve is. You've got to look for something that's up here, so it's actually down quite a ways, actually. Maybe more like 60 miles an hour. Well, if we're to bump back to 60 miles an hour in my graph, now all of a sudden we're more around the 4,072 foot-pounds of torque at the rear wheel. So we'd be able to go back like this. 72 foot-pounds of torque times 5.8333 is going to be 419 foot-pounds of torque at the rear wheel. If we come back to the CRF chart that I plotted, well, you're more like 300. So if we compare the two, I'm over 100 foot-pounds of torque more, at 60 miles an hour roughly than the CRF 450 would be. That's a big difference. Yeah, my bike's heavier, so I'm not going to deny that. The electric stuff is going to get there. In fact, I have racing cells here that I could easily put in that bike and make it lighter than a factory 450. I wouldn't be able to do more than probably 1 or 2 laps on a motocross track, but they would make it do an insane fast lap or 2. Those cells are for drag racing. They're not really ideal for a motocross bike, so to speak. They're pretty good, but they have a lower cycle life, so they're not really great for that. What I really wanted to do, though, is talk about the torque and the difference of the torque in different applications, and understanding that torque in a gasoline engine has this really weird curve to it. It's not flat like it is in an electric. And with an electric, when you're coming back to that, this is a IPM motor, so basically very much like the Tesla Model 3 rear motor, where they call it a internal permanent magnet switch reluctance motor, and it has a switch. All internal magnet motors, IPM motors, what it is the laminations in the rotor have a smooth outer surface in most cases, and then they have magnets slid inside the lamination. So the magnets aren't actually on the surface; they're down inside, and they work together with the iron in the laminations to create a surface for the electromagnetic field from the stator to pull and push against. So it works in conjunction. This does make for a little bit of a different control algorithm. You actually usually need to shift the timing around and stuff to take advantage of it. We've done an extensive amount of research in it with Axiom, our motor controller, which has maximum torque per amp working for it. So it's a section of code that basically lets us change the timing based on the inductance difference. And then we also have field weakening that actually works together with it. In SevCon, what they do is they actually have IPM lookup tables, which are basically a special table that gets mapped out by SevCon themselves for a specific motor, and it applies different amounts of timing, advance or retard, depending on the RPM and the throttle or the torque command and all that stuff. So to talk about all this, yeah, the electric motors produce full torque from 0 up until around where the torque falls off is usually where your horsepower peaks. But notice how the horsepower now stays almost flat. This horsepower curve would probably actually be pretty damn flat to about here if I didn't have parasitic losses for my drivetrain, which is my jack shaft housing. The bearings are a bit tight in there, so it doesn't spin super easy. The rear wheel bearings, the chain drag, the brakes drag, you know, the two sets of chains on there, the one on the motor, the one on the jack shaft to the rear wheel. All that stuff adds some drag to it, and even a bit of drag in the motor itself. And the tire flex on the tire on the dyno, I always run it at max pressure, but it still adds to it. And then how hard it's strapped down, all that stuff. So that that horsepower curve after the peak of after the torque starts to fall down. Notice the torque doesn't just fall off a cliff; it slowly goes down. This section is called constant power, and what it is this is where your field weakening, where the timing starts to shift in the stator, between the stator and the rotor, and it starts to fire the electromagnetic fields earlier or later. It shifts them around to actually extend the power curve out. Usually you'll get to a point where you're actually got the back EMF above the voltage of the battery pack, but what they're doing is they're turning the motor essentially into a boost converter at that point. Normally electric motors, three-phase electric motors, combined with a controller, work as a buck converter. So it takes the battery voltage, and it takes a certain battery voltage, battery amperage, and it does a buck conversion where if it's applying 105 volts to the motor and 10 amps, this is 105 volts out of the battery and 10 amps out of the battery, it'll actually buck convert it, and it could be something like 10.5 volts in the motor and 100 amps in the motor, in the phase windings in the motor. And that's kind of how a buck converter works in short. So once it gets past that point, once it gets into field weakening, it starts to work like a boost converter. So that's another thing. This section where the horsepower peaks and then it slowly falls down or stays fairly flat. You'll see this in Tesla Model 3 dyno videos and stuff too. This section is kind of like if you had a transmission in an internal combustion engine and it starts to shift up in gears. But notice how I'm already at half my speed roughly, just past half my speed where that starts to happen. I've accelerated it with full torque. Remember, torque at the rear wheel is your acceleration. It's how fast you accelerate. So I'm able to accelerate as hard as hell to half speed. And then from there, my transmission, if you wanted to call it a transmission, the field weakening works kind of like a transmission and slowly shifts you up in speed to give you more speed, but applying a little bit less torque to the rear wheel. So your acceleration is slowing down very gradually all the way up to max speed, and you still have max power. So it's actually a really neat trick, and this is why a lot of people who argue that you need transmissions for electric motors in electric vehicles, they really don't know what they're talking about. The real short answer of this is, the really short explanation of transmissions in an EV is, rather than adding the transmission with extra gears and all that stuff, you take that same size and weight and add it to more motor. You make a bigger motor. And then you do this. You do the field weakening. You change your overall gear ratio to get the acceleration you want to the speed you want. And then you have field weakening to get the top speed you want. And it makes a more efficient, more reliable system. So it means you'll go further on a battery charge, but it means you'll have less things to break, and it'll be more reliable. It'll be more enjoyable too. Like, my bike is always in the right gear. I don't care how fast you're going on my CRF. You hammer that throttle and you're begging to die. Like, it's insane how fast it is. There's nothing about it. Like, there's no way I could gear it to be any better. If I geared it faster, well, it's already got too high of a top speed. If I gear it lower, the front end's already in the air all the time. So it's perfect. There's no making it better power wise. I want to work to build the next bike to be a little lighter. That's all I'm trying to do. Coming back to horsepower and torque, if anybody's still with me here, horsepower versus torque, people talk about this, like horsepower is what, does this, and torque is how far you go into the wall, and this and that. They're basically the same, not the same, but torque is a twisting force. If you imagine a torque wrench, for those of you who are mechanics or whatever, and you pull, or a ratchet or whatever, and you pull on the handle, but it's not moving, you're applying torque to a bolt or whatever you're applying torque to, but there's zero power, zero work being done. Power is a measurement of work. So once you add motion, that's where you start to see power. So if I was to draw a line from this horsepower curve right down to zero speed, you'd actually see right here at zero, this line lines right up. Your horsepower comes down to 0 horsepower at 0 speed. You can still have 110 foot-pounds at 0 speed, but because there's no motion, there's no work being done, you're making 0 power. You need motion. So basically it's how fast something is spinning or how fast something is moving for horsepower. So horsepower is king, or power if you want to call it that, if you're talking kilowatts. You can always change your gear ratio to get the torque you need at the rear wheel, as long as you have enough power, horsepower, kilowatts, whatever you want to go by, whatever metric you like. So 58.58 horsepower peak that I have with this bike, I have enough power that I can put the gearing that I want in it, and I have the acceleration and the top speed that I want. So torque at the rear wheel is what makes you accelerate, but sometimes if you have like if you're dealing with an old two-stroke that's really high revving, like I have a shifter cart here, and the two-stroke that came out of it would have been a high revving peaky power band, you'd actually have to change, you'd have to have the right gear ratio to get it into that peak of that horsepower and get the acceleration you want. And that's why they have to run transmissions too, because they have to try and keep it at that peak of the horsepower. Hope that, or peak of the torque curve, I should say. I hope that helps everybody a little bit. Oh, one other thing, I saw in the Stark Varg thing, I won't go into it right now, but they're talking about 600 and something, high 600s foot-pounds of torque. If you remember my number for like 110 foot-pounds of torque at my rear wheel times my 5.83333 reduction is 641 foot-pounds of torque at the rear wheel. I think they're claiming 680. Somebody thought that was too much. It's believable. I don't see a reason that's not believable. I have a hard time believing that they make 80 horsepower and they can run a full motor and they weigh less than a 450. I think that's too optimistic, but we'll wait and see. I want to see somebody who dynos it and we actually see some real numbers. I've got friends who claim that they think around 11 kilowatt hours worth of battery pack is what you need for an electric motocross bike to make a full main event motocross for the pros. I wouldn't deny that. I haven't really tried to run a moto on my bike yet. I'm gonna try and get in shape for this coming season and see if I can get out to the track and put some laps on and see what kind of range I get on the actual motocross track. I definitely got a ways to go with all that. Just recovering from my spider bite and everything. Now I'm starting to feel good again, so that's good. And the other one I saw in the Stark Varg, I think Facebook group or something like that, they're talking about a high torque number, like 150 foot-pounds of torque or something, or Newton meters, I can't remember, at the motor. But what that actually is, and I believe what that is it looks like they're running a very much the same motor that Alta had, which is something like 15 or 30 foot-pounds of torque. It's not a lot of torque at the motor, but it revs high. It spins like 15,000 RPM. So what they're probably doing is when they claim the torque of the motor, it's actually with the first stage of reduction. If you look at the, if we bring up the, it'll be easier to do the Alta motors transmission. And then look at images, motor. If we can find, yeah, here. This is exactly what I wanted to show. If you look at this image here, hopefully maybe that'll let me actually jump in there and see that picture a little better. Powertrain, if we can get in there. So basically what I mean by that is at this jack shaft, at the actual front sprocket, not the rear wheel, but at the front sprocket, they're probably producing that 150, whatever it was. I can't remember the number, is up there anyway. Notice how there's like probably a 20-ish tooth sprocket here, and then the same as a clutch basket, like a 60-ish tooth sprocket here. I'm not counting them right now, I don't have the time. So what they're probably doing is they're claiming this whole thing here to be a motor, including the first stage of reduction. The Stark-Varg looks like it looks like it shares a lot of the same design, overall design. It might not be exactly the same, but it's kind of like a, you know, somebody looked at this and thought it was a good design and they kind of copied it. And potentially even the same motor or the same motor manufacturer, because Alta Motors didn't develop their own motor. They is a company in Malaysia, no, Thailand, who developed the motor, I believe. Sorry. So nonetheless, they probably got the guys who developed the motor to make a few little tweaks so they could produce a bit more power with it. And I don't know if they carbon wrapped it. I'll have to look into that, but that's something that a few people have been doing. I know there's a company down in the Bay Area carbon wrapping zero motors so you can spin them faster. And then Tesla's Plaid Model S actually has a carbon fiber wrap around the actual rotor too, which actually holds it together. If anybody hasn't watched the Sandy Monroe video, you should watch that. It goes into it quite a bit. I'm not gonna go on about this too much longer, but all I'm getting at is when they made that claim about the torque being pretty high output of the motor, I think they're including this first stage reduction. So they might have 30 foot-pounds here, but once you go through like a 3-to-1 reduction, well, you know, 30 times 3 is going to be 90 foot-pounds at the shaft, so maybe it's a 4-to-1 reduction. That puts it at 120 or something. I don't know what the reduction ratio is. We'll find that out soon enough. Anyways, I hope that helps everybody. I hope all this helps make sense. This is just a rough ballpark, kind of really crude way of showing what the torque at the rear wheel, this blue line here would be the torque of the rear wheel of a CRF 450. And that also represents acceleration. This is second gear, third gear, fourth gear, fifth gear, right? So, you know, this first, second, third, fourth, fifth, and then it's going to fall off to nothing. So that should help a lot of people understand, like, gasoline motocross bikes produce a crazy amount of torque at the rear wheel too, but it's because of the overall gear ratio, which is about 18.2 to 1 in that 450 in first gear. Anyways, stay tuned. I got lots of exciting stuff coming, and hopefully this helps everybody.